Welcome everybody in the lecture hall. Welcome everybody on Zoom. Welcome everybody from the future. So the program today is that we are going to continue the SQL brush up. And then we are going to look at cloud storage. Let me make sure that you can hear me because the audio is not always set up well. Very good. So I will start with a few questions to you, and I'll show you also the magic box and the JSONiq quickly, and then we'll start with the material. So let me share over here. Yes, so let's answer as quickly as possible. This is one that normally you will figure out. I told you about fundamental shapes of data. So which one of these is not a fundamental shape of data? Cubes, tables, trees, or circles? So you can either go to the Edu app from the App Store or the Google Play, or you can go to Edu app-app1, as you can see on the screen here, edu app-app1.eth.ch. So let's see. You said circles, and indeed, we will see some circles and rings in Dynamo, the cloud storage, but indeed, this is not a fundamental shape of data. Cubes are a shape of data. Data cubes are actually very well known in business analytics, and tables, of course, are absolutely fundamental. Here's another one. This one you might not know, but at the end of the lecture, you will know. What data shape does one typically get after denormalizing a table? I told you we are going to break all the rules in this lecture, and we are going to drop all of the relational rules. But in particular, what's going to happen if we drop all of these rules to get into the world of NoSQL? Do we get cubes, trees, graphs, or text? Aha. It turns out that we get trees. This is what we get. If you denormalize the table, you're going to get collections of trees. And this is what gives the NoSQL paradigm. But we'll spend a lot of time on this during this course. Just a question on the exam magic box. Who tried it out? And did it work for you? So you know that we set up in the chat, the element chat, we set up a channel just for Docker support. So if you have any problem, now is the moment to test it and let the TA team know, and they will try to support you. Very often is the same kind of problems that people get into. Okay, so that's actually a good sign that for most of you, it worked. And for some of you, you just got the trick of deleting the images, deleting the containers, then deleting the images, and then deleting the volumes, and then Docker Compose up, and it works. All right. All right, and some of you have issues, please let the TA team know, right? Go to the Docker support chat or send an email, and you will get some support. What's nice is that now the Apple Silicon chips seem to be working. A couple of years ago, these were the ones that were causing problems. Just so you see what it basically looks like, there will be also a tutorial for JSONiq that was a popular demand of the previous years, that instead of dropping that onto you in the last week or towards the end of the semester, we do it throughout the semester. It's just a notebook that you will find. There's a link that's basically on GitHub, and you just drop it into the notebooks folder in the Jupyter notebook, and then it should just work. You know, this is just connecting to the server. Rumble is actually part of the Docker. It's inside the Docker, and then it's connecting to that port. Basically, what happens is that all of the queries that start with %% JSONiq, it's called the magic in the Jupyter, this is going to be shipped to the server, and the answer is returned there, right? What's new this year is the syntax highlighting. Because David Buzatu, who was my master's student, did his master's thesis, he actually implemented it all, and now when you type JSONiq, you will see the highlight of the keywords, right? Now, what you see on my screen is actually a newer version because that's Jupyter Labs. You should get the update of the Docker soon. I think the current Docker you have is the older Jupyter notebook. The main difference is that it's more convenient to navigate on the left. That was also your predecessor last semester who had asked to have Jupyter Labs, right? And here you'll find all the past exams. So it's basically just environments that give you a snapshot of what you have at the exam. We will also share the 24th fall notebook for you so that you will know in advance what environment you will have at the exam, right? So this is so that you can work on all the past exams as well. I made a mistake on the exam. I told you it's in August because I keep confusing somehow the two periods, but of course the exam is January, February, right? It's in somewhere between the 20th of January and the 14th of February, if I'm correct, right? The date will be known towards November, December. Is there something else? There was also pending questions on Zoom, I think.
There's one question. One student asked whether you could explain the graded quizzes again.
Yes. So basically, we have a bonus point system. You get an opportunity to have plus 0.25 points at your exam. And the way this works is that you will get 25 quizzes. Each quiz, if you pass it, gives you plus 0.01 points at the exam. It's stochastic because it's all rounded, right? So basically, it gives you a certain probability of getting a grade increase. The way we do it is we take the Moodle raw grade out of the number of points of the exam. Then we convert it to an ETH grade, but unrounded. So just a raw grade between 4 and 6, but that can be anything. Then we add the bonus points, and then we round to the nearest quarter points. That's how it works. So the more bonus points you have, the higher the probability is that you're going to get a higher ETH grade at the end, right? So that's the quizzes. That's not the same as the exercise sheets and solutions, which are totally ungraded, right? So this is just independent of this. And I was confusing with German, unabhängig. And then what happens is that you get the quizzes in Moodle. These are Moodle quizzes, multiple choice questions, completely computer assisted. It doesn't mean that all it's automatic. If you disagree with the grading or you think your answer should be accepted, then you can engage into a conversation with the TA team and give your arguments. It's a good exercise also for you, to argue and explain your reasoning. And maybe you convince the TA team to grant points for some answers. Then, of course, we grant it to everybody else with the same answer. All right, did it answer your question? Yes? Okay, and I think it starts this week, right? Last week, there wasn't anything graded, I think, and this week you get your first graded quizzes, right? So it's going to be 2 per week, typically. And you see the passing grade is given to you, and if you have these points, you pass. Typically, what we do is that we allow you 1 or 2 attempts. If you really want to try again, then you need to email the TA team to be able to have more attempts, right? You will have 1 week. The reason we do that is that we used to give unlimited attempts, and then students just use brute force to try out all possible answers until it passed. And of course, we don't want to encourage that. The goal of the quizzes is for you to learn the material. Okay. So yeah, that's for the magic box what I wanted to tell you. Here's another one. What do you think there is in a data center? It's top secret, nobody knows. Or maybe it's one super big machine, that's what we call a supercomputer, with 1,000 core CPU, 100 petabyte disks, and 1 petabyte of RAM. Or is it plenty of small cheap machines? Or is it some sort of giant quantum computer with an array of 54 qubits? What do you think? I don't even know if 54 qubits is giant anymore. I think it's there's bigger quantum computers than that now. Okay, let's see what you said. Yes, the majority is indeed correct. Plenty of small, cheap machines. That's the secret of the data center. And I'll explain, of course, why that is. Now, I realize I should have asked you that question before the other question, but now you're probably going to figure it out easily. So when we started building electric cars, how did we design the batteries? Because you have a scaling problem with the number of batteries, right? So what do? You completely redesign the engine, you design a battery that would have more range, you assemble plenty of cheap, widespread, standard 18650 batteries. Hint, 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 the previous question. Or maybe some of you know and can't tell us. Well, okay, I think that's a pretty clear majority here. So you see, this is a widespread way of scaling up in life. It's not just for data centers, it's not just for batteries. You just assemble plenty of small and cheap components, and we'll see that's called scaling out. Okay, do I still have questions for you? I think I marked this one as correct too. Well, not yet. This I first need to give the lecture for you to tell me if you understood it. So let me now. That should be the one. After a while during the semester, the PowerPoint files start accumulated dangerously on my machines, and they get harder to find. No, that's the one. All right. So where were we? Well, first, this is data independence, right? It's very important. It's the idea that we decouple the physical layer from the logical layer, and that we look, in the case of relational databases, we look at tables, we manipulate tables. Everything that you see at the bottom, the physical storage, is completely hidden from the user. Could be a data center, could be a quantum computer, could be DNA, could be little elves in Antarctica, it doesn't matter, as long as you get the relational model on top. The second thing I told you is that when we define the relational table as a collection of tuples, collection of records, we have three constraints. The first constraint is that all the attributes are the same for all the tuples, so that you can assemble it nicely into a table shape. That's the relational integrity. Domain integrity means that in every column, it's the same type of data, right? We'll define type during the semester, but all integers in a column, all dates in another column, and so on. And then the atomic integrity means that you cannot have a table in a table in a table in a table. You cannot have objects, arrays, and so on inside. And when you have these three rules combined, that's the beautiful world of good old SQL. And if you drop these rules, you get no SQL, which we will do during this semester. Then this is what you had to learn by heart. Select from where, group by having, order by limit of sets, and you'll get plenty of exercises to learn to write SQL like this, right? So it does everything. You have the selection in there, the projection, the grouping, another selection with having, and you can order, because you have list of tuples semantics, you can order the records and paginate with limit and offset. All right, so that's SQL. And then SQL is actually much more powerful than just that. You can even nest queries in queries in queries. So just like you can have tables in tables in tables in tables, if you break the rules, in SQL, you can also have queries in queries in queries in queries, right? So you can nest a select from where inside of a from clause. You can also nest them inside of a where clause. The typical use case is to compute an argmax. So you basically have this select from where the value is equal to, and then you have a select from where inside that computes a max. That basically is a way to compute an argmax. So you can basically nest the select from wheres into the select from wheres. Okay, it can get very, very complex. And in fact, you can build gigantic queries like that. There are people who have queries of hundreds of lines like this very easily when you have an advanced use of SQL. All right. So you should practice. Take the Jupyter notebook of this week of exercises and make yourself familiar with SQL. It's really a fundamental language. Any data scientist has to know SQL, even every computer scientist. Okay, and we'll see it again during the course. Now, what happens when we do the math is that this relational algebra is also known as the Greek letters. So for people in finance, Greek letters have to do with options and futures. But for computer scientists, the Greek letters have to do with sigma for selection, gamma for grouping, pi for projection, and so on. We can write a lot of beautiful mathematical formulas that express the transformations that we do in tables. But we are fortunate enough that this is just the same thing we do with SQL. So SQL is the way to program it. And behind that query, this is what's actually going on. So the relational database management system is converting your SQL query to some what's called a tree of iterators, also called the query plan. It might also rearrange things in order to make it faster, but because of data independence, you don't have to worry about that. It's just magic. And then it executes and spits out the results to you. All right? Something else that is interesting in the world of SQL is that logic is 3 values. There's true, false, and unknown. So it means that you can extend these truth tables with a 3rd value, unknown. It's just common sense, right? False and unknown, false or, so here it's or, you can do the same with and. False or unknown is unknown, but false or, true or unknown is going to always be true. Right? It basically means that unknown can be replaced with anything and the value is always true. Right? So it's just common sense, but basically you have the 3rd added value, and that's a very important feature of the SQL language. Unknown can kind of be put in perspective with null, right? It's kind of the same, it plays kind of the same role. Okay. Then there is a bit of vocabulary. DML is a data manipulation language. That's the very generic name for a query language that manipulates data. So this is selection, projection, and so on. That's DML. DDL is about the schema. This is when you define the columns and the names of the columns and the types. That's called DDL, right? SQL has both. You can both define the columns and you can query the data and insert data. So that's kind of the difference between datas and schemas, right? And we'll also insist on that difference between data and schemas during this course. Okay, so DML, DDL. What's also good to know, I'm really very quickly going over this. In a relational database management system, what you also have is an index. An index is something magic that accelerates the query, and you just notice it's faster, but the results are the same. It's similar to what you have at the end of a book, where you have an alphabetically sorted list of words, and that gives you the pages on which you find these words, right? You've already seen that. But it's the same thing we have in database systems. We have these sort of structures that are hidden from the user, and they bring a query down from hours of execution to just milliseconds. So it's extremely powerful. Okay, we'll look into them again as a brush up in a couple of weeks in the context of document stores. Something else I want to throw at you, just like that, is the difference between 2 scenarios that we have in databases. We have scenarios where we are read intensive, we read a lot of data, and scenarios in which we write a lot of data. The scenario for writing a lot of data is the use case of a web shop where people keep placing orders. So that keeps updating the database when orders are placed and the inventory evolves. That's called OLTP, online transaction processing. And in big data, what we see a lot is the systems in which we don't really modify the data. You just download your data set and don't touch it. You just query it. That's also called OLAP, online analytical processing. And that allows us to basically denormalize the data. This is the denormalization we do a lot when we just read without writing to the data. That I'll come back to, right? OLAP might be known in the context of data cubes, but it doesn't have to be with data cubes, right? Okay, so this is, again, this distinction between writing and reading, right? But again, I'll come back to it a lot during the semester to explain that. Okay. One more thing I would like to tell you about is that when you have a relational database management system, its role is also to avoid situations like you go to the ATM and the amount is debited from your account, but you're not getting the banknotes. This is the sort of thing that can happen if you don't implement the database well. But fortunately, in these kind of systems, we have some guarantees, like in PostgreSQL and all these good old systems, that give you 4 things: atomicity, consistency, isolation, and durability. If you look at the initials, that's ACID. That's how you remember it as an Eselsbrücke. So this is, these are the 4 properties. So very quickly, this is what they mean. Atomicity means that when you have a transaction, either all of it is applied or none of it. So either you get the banknotes and it's debited from your account, or you don't get the banknotes and it's not debited from your account. That's atomicity. All or nothing, but you don't get half of it only, right? It's either all or nothing. So that's atomicity. The second one is consistency. It means that if you have some constraints on your data, the fact, for example, that your account balance should be positive, or the fact that if you have booking in a plane that no 2 people are on the same seats, you know, that kind of things, the database also guarantees that. That's called consistency. And every time you have a transaction at the end, it's guaranteed that it's still in a consistent state, right? That's called consistency. Then the I is isolation. When you log in to a booking system, like to book places, seats in a flight or in a train, it feels like you're alone, right? There's actually thousands of other people who are connected to the same website and also trying to book seats, but it feels like you're the only one on earth on the website. If that feels like it, then this is because of the isolation guarantee of the database. It supports thousands of people at the same time connected to the database, but it makes you feel like you're the only one. How? Because you do not see what the other people are doing. They might change the data, but it's made invisible to you. So this is called isolation, right? So this is also a very nice feature of the good old databases. So they support scale up in this way. And durability means that if you paid money in order to get a seat aboard the train, then you basically hope that when you actually go to the train on the day you booked it, the seat is actually there and nobody's sitting on it, right? That's called durability. It's broken when, for example, if you have an electricity problem or the computer crashes and so on, you lose the data, then you don't have durability. Durability means if you update the system, then that update is going to persist. It's staying there, right? That's durability. The 4 together are called ACID. We will see that in big data, it's actually not possible to guarantee these properties anymore. It's actually very hard to do on very large scales. There are people who try to do it. So that's the sort of things that you can implement on a single computer and that you have in PostgreSQL. But in big data, we are going to change the paradigm and actually drop also these kind of properties. But I'll come back to it. Okay, so that's ACID. That's what PostgreSQL gives you out of the box. So where does that leave us, right? So this was the brush up on relational database management systems and SQL. It's something that is typically taught at the bachelor's level. If you do not have such a course, don't worry, just learn SQL and learn these words on a high level. I will anyway come back on it during the course, right? But basically what's now going to happen in our course, you already know we're going to break the rules of the normal forms and so on. But most importantly, we're going to look at tables that have lots of rows, millions, that's still small, billions, trillions of rows. We can have quadrillions of rows. This is big data. Or we're going to look at tables that have lots of columns. In a typical relational database management system, you have a couple of hundreds of columns at most in a table. It's typically limited to 255 or 256, right? But you can also have cases in which you have millions of columns, right? You might have billions of rows and millions of columns, and it's all very sparse. A lot of the cells are empty, but that's also belonging to big data, right? So lots of rows, lots of columns, and the third one, the third dimension, lots of nesting. You can have a table in a table in a table in a table at plenty of levels. So these are the three ways that we go towards big data on the model. Lots of rows, lots of columns, lots of nesting. Basically, if you look at the rest of the lecture, this is more or less going to be every week one of these three or two of these trees, right? So for example, object storage is going to be lots of rows. So the same for distributed file system, syntax, a lot of nesting with XML and JSON, column storage, both of them, lots of rows and columns. Data models will do it with a lot of nesting, tables in tables, massive parallel processing, lots of rows, document stores, lots of nesting, but also lots of rows. I could also have put that here, and the querying for nesting. Why? Because without nesting, that's basically SQL. But we'll see how we can extend the querying paradigm when the data can be nested, and this is then a language like JSONiq, right? There's other languages, but if you learn JSONiq, you'll be able to very easily master the other ones too. So that's the last slide of the brush up, and now we are going to get into the real material with cloud storage. Do you have any questions? Anything you want to ask? Yes, over there. So let's try with we have this catch box, it's called. So
testing. Okay.
Yes.
So I guess like in this course, we consider tables to be more of an abstract data type rather than like an actual concrete data structure that we're using. But this is also an abstract data type that I guess denotes into like sort of this relational notion that you talked about before. So there's, I guess, two levels of abstraction that we're considering here that have their own sort of specifications.
You could view it that way. So basically, it is indeed a logical abstraction, the notion of tables. You don't find tables well, you do have tables like this, right? But you don't have relational tables out there. So it is really a logical abstraction in our head, right? But the reason we use it is that it's very natural to most human beings to have structure that looks like that, as we saw on clay tablets. So it is true that this is a model. It's an abstraction, and then you have the implementation of that model and the way so I didn't cover that in here, but the way it's implemented is just as files and directories on disk, right? And you put the data in the files and directories, then you parse them back as tables. You can do the same thing with trees. You can do the same thing with cubes, with graphs. It works exactly in the same way. You really have this abstraction of the view over the data and the physical implementation on disk. Right? Does it make sense? Yeah. All right, you're welcome. Anybody else? Questions? Yes?
I wanted to ask more about the definition of consistency within the ACID model. Does this mean that there are like certain like logical predicates that you can say are like a precondition before a transaction that holds on a database, and then you do something and then it holds afterward? And like, what is it that you can actually, how strong are the things that you could say about a database in these before and after predicates?
Mm-hmm. So that's the right way to look at it. You can see consistency constraints as preconditions and post-conditions that hold. But it's not just like when you think of preconditions and post-conditions, for example, in the design by contracts in programming languages, you might have different preconditions and post-conditions depending on the function you look at, right? But here, it's an eternal precondition and post-condition. It basically means that whenever you're in between transactions, before a transaction, after a transaction, all of these predicates need to hold, right? Likewise, looking at it as a predicate is the right thing to do. In fact, you have syntax in SQL that allows you to specify these predicates. You can add to your schema a predicate and ask the system to guarantee that predicate for you. So you know that when you have a transaction, at the end of the transaction, the predicate will hold, or you will get an error, right? But it will not let it happen that this predicate no longer applies. Right.
So just to elaborate on that, when you talk about a consistency definition, is there a set of like default predicates that are assumed in that kind of definition in colloquial speech?
In addition to the user-defined predicates.
Exactly, yeah.
So I would say yes, because if you consider the rest, the fact that you have an instance of the model like this, with these three rules, you can also squeeze them into the predicates if you want. You could also consider them built-in predicates, right? Just to illustrate that, if you do not have data independence, meaning that you go back to the 60s and people write the data as CSV files on their drives, then you could break the predicates that it's actually a table by writing non-well-formed CSV. You might write a CSV file, but you make syntactic errors in that file that you try to write manually. But if you use a system that takes care of it for you, you're guaranteed it's never going to create anything that is non-well-formed like this, right?
So this well-formed guarantee would fall under the umbrella of the C in ACID. That would be part of consistency.
You could consider it that way. Yeah,
Okay,
you could
all right.
consider it that way.
Thanks.
Very often when people talk about consistency, they very often refer to the additional user-defined predicates. But I think it also makes sense to consider the built-in constraints as well, right? Something that I could add is that during a transaction, it might be that temporarily a predicate will not hold, as long as at the end of the transaction it holds. But during the transaction, it's permitted to temporarily break a predicate, right? Does it answer your question?
Yeah.
Yeah. All right. Any other questions? On Zoom? All right. Very nice. And let's go on to the next part then. I just need to stop the recording cleanly here. See on the other side.